All right, so we're starting to get into structure of polymers, but before we get into structure of polymers, we have to do some basic organic chemistry stuff. And we're going to start talking about organic compounds. And the simplest organic compounds are mixtures of carbon and hydrogen, or otherwise known as hydrocarbons. This pen is so fun. All right, so hydrocarbons, compounds of carbon and hydrogen, simplest organic compound that we can think of. We want to kind of think about carbon and how it's going to behave when it mixes with hydrogen, basically. And if we look at the shell model with the orbitals, and I remember now very distinctly my high school chemistry teacher, Mrs. Safner. When I'm doing this, it's kind of funny. And I'm not drawing it very well, but hopefully you guys remember this, and hopefully you guys know what I'm talking about, so we can kind of write it out. So Hund's rule, and I've done kind of a poor job drawing these boxes. I apologize. And if you haven't noticed, I'm doing some new technology for myself here. So it's giving me a lot of, you can do this. And I can say, got it. But let's draw the orbitals in the different shells. So this is Hund's rule, and I'm drawing it a little bit better than I had before. And we have the spin, okay, of the electrons. And I've given it an extra spin, or giving it an extra electron. I'm an alchemist or something. Sorry about that. All right. So this is the 1s shell, 2s shell, and the 2p shell. Okay. So something interesting kind of happens. And we get this sp hybridization, and I'm going to talk about sp hybridized orbitals in a little bit later, or sp3 hybridization, excuse me. sp3 hybridization occurs particularly in the case of hydrocarbons. Carbon by itself also will exhibit a sp3 hybridized state as well when it comes in contact with other atoms. This is a single carbon atom. We can take a look at methane, and that's a CH4 natural gas, as it were. And the orbitals, the orbital state changes when we have carbon in contact with 4 hydrogen atoms. And so we can rewrite it in this way, where we have carbon and 4 hydrogen atoms. And so let's draw the Hund's rule for methane, CH4, the orbital boxes. The real word escapes me, and I'm embarrassing myself, but my memory isn't what it was. 1s, so we no longer have a 2s shell when we have sp3 hybridization. We have this kind of structure. And let's see if I can draw it well. I can't draw a cube to save my life, and I even have these guards, so it's almost embarrassing. Let me draw it a little better, and I'll use the template I've set for myself. And I will use this rainbow for hydrogen. Oh, it's not rainbowing very well, but anyway, hydrogen. And so I'll draw the arrow now for my carbon atom. And then the hydrogen atom contributes this electron. And so this isn't S or P, it's an sp3 hybridized. And I call it state. I may be butchering what it actually is. So you have to kind of think about this when we start talking about hydrocarbons, you know, how these shells are going to be filled according to Hund's rule. And so the first hydrocarbon we're going to talk about is an alkane. An alkane. And an alkane, you have a single bond between your carbon. So you have all these other states that need to be filled, if you remember how we're filling up these shells here. Okay, and hopefully I'm explaining it in a way that doesn't sound like a Neanderthal. I'm trying to explain things. So an example compound of alkane, or an example alkane compound, is ethane. And so ethane is C2H6. So every carbon atom now has 3 boxes to fill. Okay, so it's going to have a single bond. So one of these boxes is going to be filled up by a carbon-carbon bond, and the other boxes are going to be filled up by a carbon-hydrogen bond, basically. So an alkane, single bond between the carbon. Ethane is an example. We can draw it like this. So a single bond. And that's an example alkane. Another example alkane is a methyl group. And that can be substituted by Me, methyl group. And that's a little bit different than ethane. And it's CH3 with an empty bond here. So this dangling bond, as it were, on the carbon, and I can draw it this way. Actually allows it to bond with something else, okay? Because it wants to bond with something else because it wants to satisfy this, I call it a dangling bond. It wants to have a friend, basically. Another alkane is an ethyl group. And that's just simply ET phone home. And it's very similar. You have another dangling kind of bond with 5 carbons. And so that's going to look like this. Let me see, with this little bond there. So 5 carbons. And let me kind of try to differentiate it from the cartoon I drove above it. Sorry if this becomes nasty. So now we have this ethyl group. And so I'm going to jump a little bit. Okay, so we're talking about alkanes, and we have methyl groups and ethyl groups. These methyl groups have this kind of dangling bond here, and it's going to want to allow it to bond with other stuff, basically. And we'll see this when we talk about polyolefins more extensively. But we have this ethyl group. And if you look at alcohols, alcohols are defined not necessarily defined, but denoted as ROH. And this R, when you see R in a, I guess, compound structure, R basically means hydrocarbon. And a lot of times in a chemistry lab, if you're working with alcohol and you have your bottle labeled, which you should always label your chemicals, we see ethanol oftentimes abbreviated in this format, so ETOH, okay? And so this R could be any hydrocarbon. In this case, the R is ethanol, so we're kind of looking at the abbreviation system that we're using for our various compounds. And so ethanol, I'm going to kind of flip this hydrogen over here and make it a little nicer. And so we'd have this dangling bond, but now the orbitals, I guess, of the carbon, if I want to explain it that way, are satisfied by this alcohol, or this OH group. If we looked at methanol, so this would be denotion of ethanol. Kind of the same thing, actually simpler, so maybe I should have started with ethanol. But ethanol would be drawn that way, and I've drawn it a little crudely, but that's okay. Kind of on the subject of drawing, since I'm not doing that bang up of a job drawing this, but you can kind of get configurations of the actual geometry of the molecule by other kind of organic chemistry nomenclature, for lack of a better term. And one thing I'll talk about, so we kind of have ethanol, is how these things are drawn. And ethanol can also be drawn this way. Oops. Okay, so ethanol, we can also draw it this way. And I'm going to start off with everything that's in a single plane. So this carbon, and not another carbon, excuse me, oxygen and hydrogen are all in the same plane, as well as this hydrogen. However, when you see a solid arrow and a not solid arrow, some sort of dash, this means that this is coming out of the screen and this is going into the screen. So the simple methanol molecule actually has a structure to it, has some geometry to it, and we'll talk more about the angles and stuff like that as we progress in class. The other simple hydrocarbon we're going to talk about, am I out of space? That's interesting, is an alkene. kind of switched colors, but that's okay. Alkene. And alkenes are a little bit different than alkanes. An alkene, there's a double bond between the carbons. One of these bonds is a pi bond, and the other bond is a sigma bond. Incidentally, this single bond, if I go back to alkane, so we have a single bond on the alkane, and that should be a sigma bond. So left that out. So my alkene, double bond, we have a pi bond and a sigma bond. The pi bond is going to break during polymerization. We'll talk about that later on in class or in the semester. One example, another simple one, very similar to what we talked about above, is ethene. And that is C2H4. And double bonds. So do we fill our orbitals? Yes, we do. We fill it with our friend, the other carbon. The third hydrocarbon we're going to talk about is an alkyne. An alkyne. And ethyne is an example. And ethynes, that's interesting. So we only have one hydrogen, excuse me. We only have one hydrogen for each carbon. And so that kind of tells us something interesting. And so the bond between the two carbons ends up being a triple bond. So you have two pi bonds and one sigma bond.